Alright, and the last section in Chapter 14 discusses regular polyhedra. So a polyhedron, singular, polyhedra is plural. A polyhedron is a solid in 3 dimensions with all flat faces, straight edges, and sharp corners or vertices. So pretty much everything that we've discussed up to this point, prisms and pyramids, have been polyhedra. Now, in this section, we focus on regular polyhedra. So what this means is that all the faces of the polyhedron are congruent, and then there should also be the same number of edges coming in at each vertex. Now, these are actually well studied in famous examples in a branch of mathematics referred to as combinatorics, where we actually count the edges, vertices, etc. And so typically when we see problems in this section, we're going to be counting different things. So there are actually 5 regular polyhedra, and they are called the Platonic Solids. Plato was actually the one who discovered all of them, and the names of them are given here. So tetrahedron we already discussed. Octahedron, we have 8 equilateral triangles in an octahedron. A cube we've seen many times already. 6 congruent squares. Isocahedron, this is actually made up of equilateral triangles, and there's 20 of them. And then the other Platonic solid is a dodecahedron, and this has 12 congruent pentagons. Dodeca refers to 12, and then so there's 12 figures or 12 polygons, and they're all pentagons. All right, and then the last thing is when we study these, we can actually count different things in them. We typically count the faces, vertices, and edges. So when we're looking at a tetrahedron, we know that there's 4 faces. Each of them are equilateral triangles. Vertices, there's 4. And edges, if I count up the edges, the line segments forming the boundaries of the polygons, there's actually 6 edges. Okay, a cube, we know there's 6 faces, there's 4 vertices, and we count up the edges, so there's 4 that are parallel in one direction, and then there's 4 parallel in another direction, so there's a total of 8 edges. Octahedron, we can actually count the faces, there's 8 of them, and vertices, there's 4 in the middle and 1 on top and bottom, so there's 6 of those. And then edges is going to be 12 if you sit and count. And dodecahedron, I'm not going to count these out, but there are 12 faces, which we already knew. Vertices, there's 20, and edges, there's actually 30 of them. And isocahedron, there's 20 faces. Isoca refers to, or I say isoca, you can say icosahedron. 20 faces, icosa or isoca refers to 20, 12 vertices, and then there are 30 edges. Okay, and so what Plato did with all this is he said, not Plato. And so another famous mathematician named Leonhard Euler, I think that's his first name, but it's Euler. He actually discovered this relationship where we can count the number of faces, count the number of vertices, add those up, and that is actually equal to the number of edges minus 2. So in the case of a tetrahedron, we add these two, that's 8. Look at edges, and that's 6, and add 2 to that. And actually, if you look at most of these, or all of them, they hold. So this certainly holds for regular polyhedra, but actually he found that it extends quite a bit to simple polyhedra. So this is any polyhedron that does not have a hole in it. So something like a torus, which looks like a donut, this does not hold, mainly because, well, first of all, a torus doesn't have any vertices or faces, but you could talk about a cube. You could have a cube where you have a hole in it, where you have like a piece cut out in the middle. and that doesn't work either. So in problems in these sections, I don't have any examples prepared for this section, but typically what you need to do is count up number of faces, number of vertices, and number of edges, at least two of them, and then you can determine the third using this relationship.